All right, so let's kind of take a look at our next lesson. So we're going to be talking about inequalities. So when we started all this, we talked about several symbols that went together when graphing and dealing with inequalities or anything else. So we used before that an open circle meant that we couldn't be there. Just like we also talked about parentheses meant that we couldn't actually be there. We used a closed-in circle to mean that we could actually be a value. We used brackets to mean that we could actually be a value. And we're going to add to this. So when we go to graph, to show that we can't actually be something, we're going to graph with dotted lines. Whereas to show that we are going to be something, we're going to show it with solid lines. And that's going to correspond to the same inequalities that we talked about before. So our less than or our greater than means that we can't actually use those numbers. So they're going to correspond to the open circles, the use of parentheses, and now it's also going to get tied into using a dotted line. Whereas less than or equal to or greater than or equal to is going to correspond to filled in circles and our brackets, all meaning that we can use it. And now we're going to use a solid line to mean that same thing. So let's kind of look at one example first. So let's say we want to graph an inequality in 2 dimensions. So like y is greater than 2x plus 1. Before, when we actually worked with these, what we said was essentially that we're going to graph it on a number line, and that worked when we were only dealing with one variable. But now that we're dealing with 2 variables, we need to actually graph this on our Cartesian plane or on a coordinate plane. So to do that, what I'm going to do is I'm actually going to pretend that there is no inequality to it first. So if this was just y equals 2x plus 1, that's what we're in effect going to graph. You can use whatever method you feel more comfortable with graphing. It doesn't much matter, but we have to have a basic idea of it. Since it's already in kind of a y equals format, it's easy enough to use our y equals mx plus b method. So we know that the intercept is 1, it has a slope of 2. So from that y-intercept, we'd go over 2 up 1, and we'd have our next point. So I plot a bunch of points. Now, normally we'd just draw a line through this. And this is where we get something different. If we have a greater than or equal to, or a less than or equal to, then that would imply that we would use a straight line because we can actually touch that line. Here, if we only have the greater than or only the less than, we're actually going to use the dashed line instead. So when I go to graph this, I'm going to mark it with a dashed line, saying that we can't actually be on that. So I now have a dashed line showing where that inequality is. Now that's just true of the line itself, but we're saying that y can be anything bigger than that line. So our answer to this is any point that's actually above the line. It'd be anything in this entire region up here. So when we go to shade it, we often will shade an entire region. So my graphical answer to this inequality is that entire shaded region above that line. And we show it's dotted to show that it doesn't actually include the line. So this is the graphical version of y is greater than 2x plus 1. So let's kind of look at another example then. So same kind of problem. We're just going to graph a simple inequality in 2 variables. So let's try y is less than or equal to negative 1/2 x plus 3. So same thing. We're going to graph it. It's already in a y equals mx plus b format. So I'm going to plot out my y-intercept and then my slope and use that as the basis for everything that we need to do. So we have a y-intercept of 3, 1, 2, 3. We have a slope of negative 1/2. So we'd be going down 1 and over 2 from that point. Can't read it or read the others. There, that's a little better. Now, when I go to fill this in, I take a look at the inequality. Since it has an equal sign to it, That means we can actually be on the line. So I should actually graph this with a solid line. So remember, the solid line says that we can actually be on that line. Now, as the final to shade, we look at this. It's saying our y value, how high up we are, is less than or equal to that value. So we're actually going to shade everything below the line. So that would be our solution. So the inequality y is less than or equal to negative 1/2 x plus 3. So that's when we're just looking at basic ones. So then our next question becomes, what happens if we have a system instead? So let's graph a system. So let's say we have something like y is less than 2x plus 1, and y is greater than or equal to 1/2 x minus 2. So now we have a system that we have to graph. And the key is that this is effectively an and statement, saying that both of them have to be true. So what we're going to have to do is graph both of them on the same axes simultaneously, and then see what region actually answers both of them at the same time. So let's go ahead and do that now. So again, I'm going to start off just graphing each one separately and gain a feel for them. So we start with y is less than 2x plus 1. That's y-intercept of 1, has a slope of 2. So we have something like that, and it's a less than, not a less than or equal to. So I'd have to draw this with a dotted line. So I have that. I'm not going to worry about shading it yet. It's often easier just to get the two lines in place first. Our second equation is y is greater than or equal to 1/2 x minus 2. So now I go to graph that one. So I have y-intercept of minus 2. I have a slope of 1/2, so over 2 and up 1. Now this one does have an equality, so this can actually be a straight line, or a solid line, I should say. Now here's where having multiple colors or highlighter or something will be very useful. So when we go to do this, our first one is y is less than that, so we would be shading everything underneath it. Our second one is y is greater than 1/2, so it would be everything above it. So what I like to do is I like to draw little arrows to help me tell where the final answer is going to be. You don't have to use this. You can shade each one separately. I'll show kind of a couple different ideas. So when I go to do this, I say, okay, it has to be everything below this one. So I'm just drawing little arrows to help me see that I'm going below that one. But it also has to be above because it's greater than this one. So the area on the graph that's actually below this equation, but above this equation is our answer. So our final shaded region is that area right there. That's the answer that supports both of them. You can also do this. I've seen people do like horizontal lines for one and then vertical lines for the other, and then you can see the overlap. I've seen people do shading on both and then using a highlighter or using a Sharpie to actually mark the final answer. You could use one color for one, another color for the other, and then the blending being the final answer. It just has to be clear what your final answer is. I like using the little arrows because then it makes it really clear when I do shade something that that is actually the solution to the problem. So our solution to this system is this region that's above the bottom graph and below this one. That's the only area where it's true all the time. And it would go on forever getting bigger and bigger. So that is the graphical solution to this system of inequalities. So let's kind of look at another one. So let's take a look at y is less than 2x plus 1 and y is greater than 4. So we're going to do the same thing. We're going to start by graphing them. Again, pretending that they're just equals, using whatever tricks we have from Algebra 1 to graph. These are just linear equations after all. So if I go to graph y is less than 2x plus 1, I just pretend it's y equals 2x plus 1. So I have a y-intercept at 1, and I have a slope of 2 again. And since this is a less than, I need a dotted line. Y is greater than 4. Okay, so remember, when we just have y equals a number, that's saying that the height is that number. So in this case, every single point that has a y of equals to 4 would actually be a horizontal line at y equals 4. And again, since this is greater than, it's just dotted. We're not actually going to fill it in with a solid. So I have my two lines. Now I'm going to go look at shading. So y is less than 2x plus 1. So it has to be below this graph. But it has to be greater than the 4. So it has to be above this one. So similar to our previous problem, the only area that's both below this and above this is this region right here. So that region would be my answer. All right, so what if they don't give it to us in that format? What if they give it to us in some other format? So what if they gave us something like x plus y is less than 2 and 2x minus y is greater than 4? All right, so this gets a little bit trickier. There's not really a good clean answer for these. So you have a couple options. We can graph it using our intercept method, which is normally how we graph it when they have it in a standard form. So let's go ahead and graph it that way. So if I'm using intercept method to graph, then I'd say, okay, if y is 0, then x would be 2. So there's 1 point. If x was 0, then y would be 2, and there's my other point. I know it doesn't have an equality, so it'd have to be a dotted line as we go along. So that's all well and good. The difficulty comes when we go to talk about shading. It's not as easy to look at that and tell, are we going to be above the line, or are we going to be below the line? And oftentimes you have to try a test point to really do it. So if teachers ever talk to you about a test point to test an inequality, what they're saying is, okay, let's choose a nice easy point here. So like this point here is 2, 2. And let's see if that actually works. So if I plugged in a 2, 2 into this, I'd get 2 for the x, 2 for the y, and I'd get 4 is less than 2. That's not true. So we can't shade above it. We'd have to be shading below that line. I'm not a big fan of that method. Yes, it does work very quickly. And if you like that, more power to you, go right ahead and use that method. I still tend to prefer to think of it in terms of the y. So what I would do is take this same equation, I'd solve it for y. So I'd get y is less than negative x plus 2. And then it's easier to tell, okay, the y is less than, so we're going to shade below. Same thing we can do here, 2x minus y is greater than 4. If I use the intercept method to graph, if my x is 0, then y would be negative 4. If y is 0, then x would be 2. And again, since there's no equality to it, we'd do it as a dotted line. And we'd get something like that. Rulers would be helpful. I'm a little bit messy there. Again, if we wanted to see if we're going to shade above or below, we'd need to test a value. And I like to test easy values. So I'm going to test 0, 0. If I plug that in, I get 0 is greater than 4. That's not true. So it'd have to be below it. Again, I find it easier often to solve for this. So if we have 2x minus y is greater than 4, I can add y to both sides and get 2x is greater than 4 plus y. I can subtract 4, and I get 2x minus 4 is greater than y. So y is less than the 2x minus 4, so we're still shading below. So again, I can draw my arrows, and the only part that's below both of these at the same time is this region right here. That's the region where we're actually below both graphs. So that would be my solution. So again, when you're looking at it in standard form, you can either graph it using the intercept method and then use test points to see where you can shade, or you can convert it to y equals mx plus b format, and then you can read it off. So y is less than, so shade below, y is less than, shade below. All right, so as our final example in the slides presentation, we have a real life example now. So we have a used bookstore that sells paperbacks for $2. It sells hardcovers for $5. Amanda wants to buy at least 6 books, but only has $20. Create a system of inequalities to model Amanda's situation. So this is just like kind of our last lesson when we were looking at common word problems that people would use while looking at systems. So again, we have a total number of items versus a price. So if I look at our variables, then let's see, we could use P for the number of paperbacks. We could have H is the number of hardcovers. And now we could create some inequalities. So our first system, it would be money. So we know that 2 times the number of paperbacks plus 5 times the number of hardcovers. So that's the cost of a paperback times the number of paperbacks. The cost of a hardcover times the number of hardcovers has to be less than or equal to $20 because she only has $20 to spend. We also know that she wants to buy at least 6 books. So the total number of books, so the number of her paperbacks plus the number of her hardcovers needs to be at least, so greater than or equal to 6. So this gives us a system. But there's a couple more things that aren't really mentioned that are implied when we're dealing with real life. We also know that P has to be greater than or equal to 0. You can't go in and say, I want to buy negative paperbacks. I mean, I guess you can kind of in a used bookstore because you can turn in books, but let's not go that far with it. Same for hardcovers. She's not going to buy any negative hardcovers. So both of these have to be greater than or equal to 0. So when we go to graph our situation here, we actually don't even need anything besides the first quadrant. Now, unlike X and Y, we need to set which of these are which. So I'm going to have my P axis here, so the number of paperbacks, and my H axis here. Each of them can only be positive, so I'm only looking at this first part. So there's no reason to include any of the rest. That's what this restriction has done. Now I need to graph each of these. So I know that P plus H has to be greater than or equal to 6, so I'm going to pretend it's just equal to 6. So that would give me a P-intercept of 6, 1, 2, 3, 4, 5, 6, and an H-intercept of 6. I'm sorry, H-intercept of 6, P-intercept of 6. So there we go. And we know that their sum has to at least be 6. So I can have a solid line going through. Now, one thing we need to be careful of here, well, actually, let's hold on. So let's get our lines drawn first. So we have it, and that sum, their total has to be greater than 6. So we could actually do a test point if we wanted, but we'd find out that we'd be shading above this region. Anything inside this region and our total would not be at least 6 books. So now we can go ahead and graph 2P plus 5H is less than 20. I might have made my axes a little bit too small, but we'll see. So again, if I do the intercept method, I can go ahead and say, okay, if P is 0, then I'd get H would have to be 4. If I get H is 0, then P could be 10. Oh, I miscounted. 1, 2, 3, 4, 5, 6. 9, 10. There it is. And again, it has an equality, so we could do a solid line. And we get something like that. Now, we know we had to be above this line, our first one, but we need to be below, or do we need to be below? That's our next question. So when we look at these, we know that P plus H has to be at least 6. So here's my P plus H is at least 6, is anything above this line. Now when I look at 2P plus 5H has to be less than or equal to 20. Well, that looks like we're going to need to be below that line. So we'd have to be below this one. And again, we could test it by either putting it into y equals mx plus b, or in this case, h is our y. So I could show that real quick, so why don't we do that? So we have 5h is less than or equal to 20 minus 2p. I can divide both sides by 5. And I'd get h is less than or equal to negative 2/5 p plus 4. And if we look at it, 1, 2, 3, 4, negative 2/5, that's matching pretty well what we have. So again, it would be under it. So our criterion here is basically that she has to be getting more than this amount, but less than that amount. So the only books that she can really purchase fall in this region right here. Now, because she's actually purchasing real physical things, we're really only looking at actual whole values. We're not looking at decimals. You can't go into the bookstore and order, hey, can I have 2.5 hardcovers? That gets kind of weird. So our actual solutions are only the points that are inside that region, nice and neat. So those values are the only ones that would actually work all that well. So as an example, 1, 2, 3, 4, 5, 6, she could buy 6 paperbacks and 1 hardback, and that would work. She could buy 7 paperbacks and 2 hardbacks. There's our 7 and 2. Now this is where you have to be careful. So when I first drew it, that looks pretty good. But I wasn't using a straight edge. I wasn't double checking my line to see how clean it is. So the question becomes, is that actually a solution, or is my line slightly off because I wasn't actually using a ruler? So we can actually check. So 6 paperbacks, 1 hardback. If we go back and check our criterion, well, 6 plus 1 is greater than 6. So that works. 6 paperbacks would be 12, plus 5 is 17, so that works. But if we try 7 paperbacks and 2 hardbacks, well, 7 plus 2 is greater than 6, that works. 14 plus 10 would be 24. So my line, because I didn't use a ruler, is actually including this point that's not actually there. So be careful when you go to draw these out. If you're trying to actually get solutions and you're just slopping the lines down, you'll get some false answers because of it. So make sure you draw it nice and neat and precisely. Definitely use graph paper to help you out as you do it. So our solutions then are anything that's directly in that shaded region, and this is why you want to be careful with your shading. So make sure that you're looking at these and actually checking to see if they work. Let's try something that, say, might not work. Let's check this point here. According to our graph, it's not an answer, but let's see if that makes sense for what they gave us. So that's the point 1, 2, 3, 1. So 3 paperbacks, 1 hardback. Well, she certainly has the money for it. That'd be 6 plus 5 is $11 is less than 20, so it works for that. But 3 plus 1 is not greater than or equal to 6, so it failed that check. What if we looked in this region here? Let's say that was the point 1, 1, 2, 3, 4. So the point 1, 4 isn't satisfying either of them based on our graphs. Let's see if that's true when we look at our equations. So 1 paperback plus 4 hardbacks is not at least 6 books, so it didn't meet her minimum requirements of books. 1 paperback and 4 hardbacks would be $2 plus 20 is $22. She doesn't have enough money for it either. So it doesn't satisfy any of them. So when you look at these points, that kind of visually and kind of viscerally tells you what is going on for the possible things that she can actually do. All right, as a final thought before I set you loose onto the homework. So we've been looking at systems, but systems of inequalities almost always are giving an infinite number of solutions. So when we went back and we looked at some of our other graphs, say go back in time to this one, anything down in this would work. So this is already an infinite number of solutions. That's not why we're not really saying it. This entire area is our solution. In the case of real life, where you're actually buying physical things, it's not necessarily an infinite number of solutions. It's just we're constrained to only certain solutions that are in our boundaries. However, we can get no solution. So it's possible that they don't overlap at all. So I want you to kind of think about that and look for it on the homework. I'm going to give you at least one where the answer is no solution. So try to keep an eye out that for the graph.